Welcome to the training module on the continuous time sigma delta analog to digital converters by National Semiconductor. This training module introduces the continuous time sigma delta analog to digital converter and National's ADC 12EU050 ADC. Analog to digital converters perform two basic fundamental operations: discretization in time and discretization in amplitude. The two functions are shown conceptually in the figure, though the actual ADC may not be structured as such. The first operation of the ADC is to discretize in time or sample the continually time-varying input analog signal. The input signal is typically sampled at uniformly spaced times at a frequency of fs, and the samples are thus separated by a period of ts. Once the input signal is sampled, the resultant signal exists only as impulses at the sampling interval. The second function of the ADC is to discretize the sampled signal in amplitude. That is, the ADC approximates the amplitude of each sample with one of a finite number of possible values. The amplitude of each sample can be represented by a digital code whose bit length determines the total number of possible converter outputs. However, the finite number of output values in a converter introduces error into the digital representation of the analog input, which is called quantization error. The different ADC architectures typically offer different compromises between ADC resolution and output sampling rate. A successive approximate register SAR ADC essentially performs a binary search of the input signal using only a single comparator. This converter approximates the input value with finer resolution each successive cycle. Because the SAR requires n cycles to produce an n-bit resolution output, the speed of state-of-the-art SARs is often limited to several MSPSs. The pipeline architecture employs multiple low-resolution flash conversion stages cascaded in series to form the pipeline. Pipeline ADCs have become the standard in data conversion applications at 8-bit and higher resolutions for sampling rates from 5 MHz to 100 MHz or more. The basic principle of operation for the sigma delta modulator is to enclose a simple quantizer in a feedback loop to shape the quantization noise such that most of the noise is shifted out of the band of interest, where it can later be suppressed by filtering. The continuous time sigma delta analog to digital converter employs continuous time circuits, often RC or C/GM integrators. Compared to the discrete time design using a switch capacitor for the integrator, the new design uses fewer capacitors, which makes it easier to speed up. The sampling operations in a CT sigma delta modulator occurs at the output of the forward loop filter, before the digitizer as shown in the figure. The CT sigma delta analog to digital converters operate at lower power, include significant anti-aliasing filtering, and present a much quieter input stage. Because of its oversample operation, the output rates of the CT sigma delta analog to digital converter are currently limited to less than 100 MSPS. National's ADC 12EU050 is a 12-bit CT sigma delta analog to digital converter. The ADC 12EU050 offers performance improvement both because of the inherited advantages of CT sigma delta technology versus sampled input analog to digital converters, such as pipeline and traditional, discrete time sigma delta analog to digital converters, and also because of additional circuitry that National has integrated onto the chip. Because of oversampling in the sigma delta modulator and digital filtering at the modulator output, a CTSD analog to digital converter offers inherent anti-aliasing filter. The ADC 12EU050 provides 72 dB of stop band attenuation which significantly reduces the required order of the filter preceding the analog to digital converter, and may even render such an external filter unnecessary. A second advantage is an input that's purely resistive. The power consumption of the ADC 12EU050 is 25% lower than pipeline ADC solutions. Here's the simplified block diagram of the ACD 12EU050. The major signal paths blocks are clipping control, CT sigma delta modulator, digital decimation, filter, 12-bit serializer, and finally the LVDS/SLVS outputs. The internal digital decimating filter provides an intrinsic anti-alias filter, eliminating external analog filter components and simplifying multiple channel designs. The PLL is critical to the operation of the ADC 12EU050, and the PLL also provides the bit and word clock outputs. The SPI control interface gives uncomplicated user access to the ADC registers. The most significant benefit of the CT sigma delta architecture is its low power consumption relative to comparable sampled input analog to digital converters in the high-resolution sub-100 MSPS application space. The power advantage of the CT sigma delta implementation arises because of the internal circuitry. In any traditional ADC, the internal amplifiers must settle to within some target resolution each period. This places significant speed constraints on the internal amplifiers, increasing the power consumption. In a CT sigma delta with CT feedback, the amplifier output never attempts to switch its output voltage instantaneously. There is no output settling required, and hence the amplifier speed constraints are relaxed and consume less power. In addition, several power management modes are provided: power down, sleep mode, and single-channel power down mode. The CT sigma delta analog to digital converter architecture eliminates the need for stringent input filtering because of its inherent anti-aliasing filter. In the ADC 12EU050, many of the performance characteristics of the anti-aliasing filter, AAF, are set in the digital domain, allowing for a very high level of passband flatness and steep roll-off. Because the CT sigma delta analog to digital converter samples at the output of the forward loop filter, the signal is first low-pass filtered by the loop before sampling, which attenuates signals around the modulator loop sampling rate that can alias down in band. Furthermore, because these aliased signals are then injected at the input of the internal quantizer, they are noise-shaped by the loop in the same manner quantization noise is shaped. The CT sigma delta analog to digital converter also allows a much quieter input than a sampled input ADC because of the CT nature of the internal circuitry. Because the input of the CT sigma delta is not sampled, there are no switching capacitors and it is easier to drive the input, allowing for use of cheaper, lower power driving circuits. In addition, the lack of input switching noise will reduce noise coupling into the system, improving its overall performance. Finally, without any switches at the input to restrict the input voltage swing, the allowable input voltage range can be higher than for a SC sampled input analog to digital converter. Indeed, the input voltage can even exceed the supply rails. A low jitter sampling clock is crucial in all high-speed, high-resolution data conversion systems to realize the full resolution of the ADC. The modulator oversampling clock in the ADC 12EU050 drives the quantizer of the internal sigma delta loop. This clock is provided by an on-chip clock conditioner comprising a PLL and a VCO. The high-performance PLL uses an on-chip LC tune circuit to create a high-Q resonator. This on-chip clock circuit multiplies up the frequency and provides low jitter sampling edges to the modulator loop, allowing for the benefits of CT sigma delta analog-to-digital converters to be realized without requiring a high-performance, high-cost external clock source. The ADC 12EU050 analog-to-digital converter solution offers 12-bit resolution at an output rate up to 5 times the fastest currently available sigma delta analog-to-digital converter. The power dissipation is 30% lower than pipeline ADCs. The CT sigma delta technology on which the ADC 12EU050 is based also offers significant inherent anti-aliasing filtering and provides a low noise, easy to drive input stage. To fully exploit these considerable benefits of the CT sigma delta technology, the ADC 12EU050 also includes an on-chip clock conditioner that eliminates the need for high-performance, expensive clocks. Finally, the ADC 12EU050 avoids the hazards of input overload presented in sigma delta analog-to-digital converters by offering a means for recovering immediately from an input overload event.